Alright, so this is problem 34.11, and the question is asking to find, for each case, determine the induced EMF, induced current, and direction of the current. The diameter of the hoop is 10 centimeters, while the resistance is 2 ohms. So for the first case, we have the magnetic field increasing at 0.5 teslas per second out of the board. So you want the B field into the board, increasing into the board to oppose this increase out of the board. So using the right hand rule, the current will go clockwise. So this will go clockwise. Now to find your induced EMF, you have the equation E equals D dt. And since only the magnetic field is changing while everything is constant, this will equal area times dB dt. So your area, so the area of this hoop is going to be pi r squared times your dB dt, which is given 0.5. So since our hoop is 10 centimeters, half of that, the radius will be 5 centimeters. So you have pi 0.05 squared times 0.5 will give you your induced EMF, which will be 3.97 millivolts. And the direction will be clockwise, and your induced current will be, you can find the induced current from V equals I R, and putting that in as V will give you 7 divided by your resistance, which is 0.2 ohms, will give you a current of 20 milliamps. Now for part B, the magnetic field is decreasing at 0.5 teslas per second into the board. So to oppose that decrease into the board, you want your induced magnetic field increasing into the board. So to go into the board, using the right hand rule, your current has to go clockwise as well. And it's the same process. You have only the magnetic field is changing. So you have your area of your hoop, pi r squared times 0.5, which is the dB dt, and this is the same answer of 3.97 millivolts, and it will also give you the same current of 20 milliamps here. Alright, so for part C, you have the hoop the hoop's facing directly at you, so that its surface will be parallel to the magnetic field, which will not give you any induced EMF, so no EMF, and therefore no current as well.